Hello everyone, welcome to this video lecture of 19ScPhyU301. We have been discussing the first chapter, complex numbers. These are the topics that we have studied so far. We have covered all the basics of complex numbers, and then we considered a few elementary functions of complex number. A common theme in all these functions is that these functions are multivalued, which means the same function of the same complex number can lead to different values, different distinct points in Argand plane. In fact, these points are infinitely many. The reason behind these multivalued function is that the same point in Argand plane can be represented by infinitely many complex numbers written in exponential form. All these numbers are such that their moduli is same, but their arguments differ by 2 pi radians, and that is why we get infinitely many answers to the same function of the same complex number. This is the last video lecture in this series for the chapter complex number. From next lecture we will start with the next chapter, second chapter. In this lecture we will see two applications of complex numbers. First one is the motion of a point particle in a plane. We will write down the relation for the position vectors, their velocity and acceleration in rectangular coordinate system and in polar coordinate system, plane polar coordinate system. The second application that we want to discuss is for AC circuit, where we will use complex number to represent an AC circuit. Let's begin by discussing the first application, motion of a point particle in a plane. Now I want to first explain why are we saying that it is a point particle. The reason is simple. If we have an extended body, then we also have to consider the rotational motion of that body, and we are not considering that case. We will be considering only linear motion of a particle, and therefore it is good idea to consider a point particle. Of course, it is always possible that we consider an extended body and then consider the center of mass of that body, and how it moves linearly is equivalent of saying that it is a point particle with mass m. So it is one and the same thing, and that is why we are considering a point particle, or we can say that we are considering that we are taking into account motion of center of mass of an extended body. When we are considering motion of a particle, we first have to start by explaining its position vector as a function of time. So this r of t is the position vector which is changing with time, and since it is changing with time, we can say that the body is moving. We have already seen that a complex number is very much similar to a two-dimensional vector. It has real component and it has imaginary component, and therefore we can say that a complex number, when written as a function of time, such that its real part is a function of time and its imaginary part is also a function of time, then this basically represents the position vector of a body as far as we are treating motion of the object or motion of the particle in a plane. So what we are saying is a complex number z, which is a function of time, represents the position vector of the particle which is moving in the plane. When we consider a complex number in rectangular form, it basically represents position vector in rectangular coordinate system. When I write z as a function of time in rectangular form, this basically is the rectangular position vector of the particle being considered. Then finding out velocity is easy. If I want to find out velocity of a particle, what I do is I differentiate its position with respect to time. In this case, the position vector r is the complex number z. Therefore, velocity can be calculated by differentiating z with respect to time, which is going to be equal to dx by dt plus dy by dt into I, where this I, remember, is the square root of -1. So this is how we can write velocity of a particle by using complex number in rectangular coordinate system. Many times a notation is used where dx by dt, or differentiation of x with respect to time, is written as x dot, and differentiation of y with time is written as y dot. So here we can write v as x dot plus y dot into I. Remember, all of them are functions of time. Acceleration is differentiation of velocity with respect to time. So it is straightforward here. If I want to write down acceleration of a particle which is moving in a plane by using complex number, then that can be written as x double dot plus y double dot t into I. Remember here that I is square root of -1, the imaginary number, and x dot means it is differentiation of x twice with respect to time, and y dot is differentiation of y twice with respect to time. So this is how we can find out acceleration and velocity of a particle which is moving in a plane by using complex numbers. This is how it can be represented. Many times it is convenient to use plane polar coordinate system instead of rectangular coordinate system while discussing the motion of the particle. For example, if we are considering motion of a particle which is moving under central force, which is moving under influence of force which is such that its direction is always along the line joining the particle and a fixed point in space, then these forces are called as the central forces. And when we are discussing motion of the particle under central forces, generally it is convenient to use plane polar coordinate system for discussing motion in a plane. In previous slides we have seen that how we can write motion of a particle in a plane in rectangular coordinate system. It is simple. Position vector of the particle, it's simply a complex number written as a function of time. Then its velocity is given by differentiation of r with respect to t once, which is x dot t plus I into y dot as a function of time. Acceleration can be obtained by differentiating r twice with respect to t, which is equal to x double dot plus I y double dot. Remember the notations here. X dot is differentiation of x once with respect to time, and x double dot here is differentiation of x twice with respect to time. We will continue to use these notations for coming slides when we discuss motion in plane polar coordinate system. For plane polar coordinate system, position vector r is complex number written in exponential form, r into e to the power I theta. Note that since the particle is moving, this r or modulus of the position vector is also a function of time, and argument is also a function of time. Suppose at some instance the particle is here and it is given by this complex number r of t into e to the power I theta. We already have seen that when we represent r, we get this circle, and when we give the argument, we get this line which makes angle, rotational angle of theta with positive real axis. And in this way we can write position vector of the particle as a complex number in exponential form. When we are discussing vectors, we have to deal with the unit vectors. For rectangular coordinate system, these unit vectors are ex. Ex is unit vector along positive x-axis and it has unit length. Similarly, along y we have unit vector which is ey. This cap here suggests that it is a unit vector. And for rectangular coordinate system now, no matter which point we consider in the plane, these unit vectors are always in the same direction. So no matter which point I consider, ex and ey are always going to be in the same direction, which is not the case when it comes to plane polar coordinate system. Let's write down the unit vectors for a point which is represented by this dot in plane polar coordinate system. The first unit vector is the radial unit vector, which is such that it has length which is equal to unity, and its direction is along the line joining the point and the origin, and it is always directed outward from the center. So it is the radial unit vector ER. This is the first unit vector when it comes to polar representation. For a point in plane polar coordinate system which is given by these coordinates r and theta, which we are writing as the exponential complex number, this unit vector ER, which is radial unit vector, can be written as e to the power I theta. You can see for this complex number that its modulus is 1, so it has unit modulus, and its direction is also radially outwards. Obviously now the second unit vector is going to be perpendicular to the first unit vector ER, which I am writing as E theta cap, and which is making 90 degrees with the first unit vector ER. Now how can I write unit vector E theta using a complex number? Note that since this is unit vector, its modulus is going to be 1, and its argument at this point r and theta is perpendicular to ER, and therefore that angle is equal to theta plus pi by 2. Unit vectors in plane polar coordinates, unlike rectangular coordinate system, are not in the same direction at all the points. They are in different directions for different points. For example, if I consider this point, ER is going to be in this direction and E theta will be in this direction. So this is ER cap and this is E theta cap. For this point, ER cap is going to be in this direction and E theta cap is going to be in this direction. Now let's quickly summarize how complex numbers can be used to write position vector of a particle in plane polar coordinate system. So position vector in plane polar coordinate system is given by exponential representation of complex numbers. This is a circle with radius r and it is making an angle theta. So this gives the position vector. Unit vector at this point is given by ER, which is called as radial component of unit vector. This ER is represented by this complex number e to the power I theta for a point which has modulus r and argument theta. The second unit vector e theta or tangential unit vector has this direction, and for a point having modulus r and argument theta, e theta is given by e to the power I theta plus pi by 2. Now e to the power I theta plus pi by 2 I can write as e to the power I theta into e to the power I pi by 2. E to the power I theta by 2, if I write in rectangular form, is nothing but I into e to the power I theta, where I is the imaginary number, and therefore this gives us the position vector in plane polar coordinate system. ER gives us the radial component or radial unit vector, and the tangential unit vector is given by this number I into e to the power I theta. One important point to remember here is that at different points r and theta, these unit vectors will have different directions. ER is radially outwards and tangential vector is then perpendicular to that. At this point again ER is radially outwards and its tangential component is along the tangent. Let's now consider the motion of the particle in plane polar coordinate system using complex numbers. So position vector r is simply the complex number z. Therefore, this is the position vector in plane polar coordinate system. How can we obtain velocity now? V of t is first differentiation, or r, differentiated once with respect to time. Therefore this is equal to d dt of r of t into e to the power I theta of t. This is equal to, I have to use u into v rule now. It is dr by dt into e to the power I theta plus t, plus I'll keep r of t as it is and will differentiate the exponential part, which is I into d theta by dt into e to the power I theta. This is equal to, we will use the dot notation now, r dot into e to the power I theta plus I into r theta dot into e to the power I theta. Now in previous slides we have seen that e to the power I theta is the unit vector along radial direction, and I into e to the power I theta is the tangential unit vector e theta, and therefore velocity is r dot into t into er plus r into theta dot into e theta. This is the radial component and this is the tangential component. Let's briefly discuss each of these components now. First, the radial component. Radial component is given by r dot. R dot gives us how quickly the particle is moving away from the center. So if I consider this direction, which is radially outward, then it is positive. If I consider this direction now, then the radial component of this velocity is negative. If a particle is moving along the tangent, then this radial component is 0, because as far as it is moving along the tangent, as far as it is moving along the circle, the distance between the particle and the center is not changing, and therefore radial component is 0. Let's now discuss the tangential component. Tangential component is given by r theta dot. Remember, theta dot is d theta by dt, which is nothing but the angular velocity, which sometimes is written by omega, and therefore this component, tangential component, is nothing but r omega. If a particle only has tangential component of the velocity, and if it has zero radial component, then the particle is moving in the circles. Distance between the particle and the center of the circle is not changing at all, and r omega gives us the velocity along the tangent, and therefore it is called as the tangential component. Let's now see how we can write acceleration by using complex numbers. So first let me write down the velocity, which is equal to r dot e to the power I theta plus r into theta dot into e to the power I theta. To get the acceleration, I have to differentiate velocity once with respect to time, which is equal to, I'll first differentiate the first term, which will give me two terms. It is therefore r double dot e to the power I theta plus I into r dot theta dot into e to the power I theta. Now I'll differentiate the second term. Second term is multiplied by I. Remember, it is the tangential component. This now is I into r dot theta dot into e to the power I theta plus r theta double dot into e to the power I theta plus I into r into theta dot whole square into e to the power I theta. So this is equal to r double dot e to the power I theta plus I 2 into I into r dot theta dot e to the power I theta plus I into r theta double dot into e to the power I theta, and the last term, since we have multiplication I with I, is negative and there is no imaginary number in there. It is r into theta dot whole square into e to the power I theta. Let's now collect the radial and tangential component. Radial component is r double dot minus r theta dot square, and since it is multiplied by I theta, it is the radial component, plus tangential component is 2 r dot theta dot plus r theta double dot into I into e to the power I theta. This is the radial component and this is the tangential component. So what we have is r double dot minus r theta dot whole square er plus 2r dot theta dot plus r theta double dot e theta. So the radial component is r double dot minus r theta dot whole square. This second term is due to the centripetal acceleration. Since the particle is going in circles, r omega square is the acceleration which is experienced, or rather minus r omega square is the acceleration which is experienced due to the circular motion. Let's now move on to the second application of complex numbers. What you can see on the screen is LCR circuit. This is a resistor, this is an inductor, and this is a capacitance, and all these three components are connected in series with a AC power supply. If the power supply which is connected to the circuit is AC power supply, then we expect that the current is also sinusoidal. Let's write this current in this fashion: I0 sine omega t, where I0 is the maximum or amplitude of that current. Now this I can write as a complex number in this way: I0 into e to the power I omega t. If we use Euler's formula, then this is actually I0 cos omega t plus I into I0 sin omega t. Therefore, when I am writing the current as a complex number like this, the imaginary part represents the actual current. Of course, there is nothing special about the imaginary part. What you can do is you can say that it is actually the real part which represents the current. So for this LCR circuit which is connected to AC power supply, we are writing current flowing through the circuit as the complex number I0 omega t. Let's now consider what is voltage across each of these components. Let's first consider the resistance. Let's find out what is the voltage across the resistance. Remember, I we are writing using the complex number I0 into e to the power I omega t. Now voltage across resistor is given by this equation IR, and therefore VR is equal to R into I0 e to the power I omega t. Let's now write the voltage across the inductor. Voltage across inductor is given by L into di by dt. Since I is equal to I0 e to the power I omega t, VL is L into I omega I0 e to the power I omega t. Voltage across capacitance now can be found out by using definition of the capacitance. C is equal to Q by V, where V is the voltage and Q is charge accumulated on the capacitor, and therefore V across capacitance is equal to Q by C. I is I0 e to the power I omega t. This is function of time, and therefore Q as a function of time can be obtained by integrating I of t with respect to t, because I is defined that way. I is dq by dt. Therefore Q can be written as minus I omega I by omega I0 e to the power I omega t. Therefore Vc is minus 1 by omega c into I0 e to the power I omega t into I. Now next step is to use Kirchhoff's voltage law, which says that V, which is the AC voltage applied, is equal to VR, voltage across the resistance, VL, voltage across the inductance, and VC, which is voltage across the capacitor. This is equal to R I0 into e to the power I omega t. This is I into L omega into I0 into e to the power I omega t, and the last term is minus I into 1 by omega c into I0 e to the power I omega t. This is therefore R plus I into omega L minus 1 by omega c into this whole term is multiplied by I0 e to the power I omega t. Remember, this is nothing but I, current as a function of time, and therefore V we can write as, for this whole square bracket I will use the notation Z into I of t. This Z is R plus I into omega L minus 1 by omega c. So this is basically a complex number. This is real part of that complex number, which is the resistance in the circuit, and this is the imaginary part of the complex number. We will discuss this Z in detail on next slide, but note that this equation now can be compared with Ohm's law, V is equal to IR, where this R now is replaced by the complex number Z. Now let's discuss what this Z is. This Z is R plus I into omega L minus 1 by omega c. This is called as the impedance in the circuit. Therefore, impedance of LCR circuit can be written as a complex number with its real part as R, which is resistance in the circuit, and the imaginary part is omega L minus omega 1 by omega c. This is called as the reactance in the circuit. The first term is inductive reactance, and the second term is the capacitive reactance. And in this way, now we can use Argand diagram to write Z. This is R, which is the real component, and what is condition on R? R is always positive, it cannot be negative. Similarly, L and omega are always positive, therefore inductance is always along positive imaginary axis, which is omega L, and capacitive inductance is always negative, it is along negative imaginary axis, which is 1 by omega L. Here we have come at the end of this lecture. This is the summary. We considered motion of a point particle, or equivalently we can say that we considered motion of center of mass of extended body in a plane, and we considered that first in rectangular coordinate system, and then we considered the motion in polar coordinate system as well. Here for the first case we wrote complex number in its rectangular form, whereas for the second application we wrote the complex number in exponential form, such that r into e to the power I theta is the position vector, and e to the power I theta is the radial unit vector, and I into e to the power I theta is the tangential unit vector. Then we also consider LCR circuit, in which we can use complex numbers to model that circuit. This was the last lecture in this series of lectures on first chapter, complex numbers. From next lecture we will start discussing the second chapter, which is partial differentiations. Thank you for watching this video.